Good morning, everyone. So first talk is by Raymon Watson from University of Queensland, Australia. And he's going to talk about non-equilibrium quantum thermodynamics via generalized hydrodynamics. Over to you, Raymond.
Yeah, so thank you for having me, and I'm really sorry that I couldn't be there. It just seemed to not really work out on my end, but yeah. Today I just want to talk a bit about a specific application of generalized hydrodynamics that I've been working on at UQ with Professor Karen Karansian. Um, and essentially, whoops, let my screen move. Okay, yeah. So I'm mainly going to be focusing on this specific application to quantum engine cycles or quantum heat engines and trying to motivate the case for why generalized hydrodynamics is particularly useful, in particular for theoretical modeling of experimental application. Okay, I just wanted to start with a really broad overview of what quantum engines actually are. Essentially, I've tried to give the broadest definition of a quantum engine as any cyclic protocol that generates beneficial network using some sort of quantum working fluid or a quantum system. So you have some kind of, in this case, for a heat engine, there are more general cases, which I can talk about, but you have some sort of working fluid connected periodically to a high and low temperature thermal bath. And it goes in some sort of cyclic operation. I'll talk more about that in a second, but essentially uses the flow of heat to generate some kind of beneficial network. And the motivation people usually talk about is either utility, i.e., we could use something like this to power nanoscale devices, or theoretically, if you were to run some sort of refrigeration cycle to cool an already ultra cold atomic gas. But also a big focus is on possible quantum advantage, i.e., if you performed the same cycle using classical resources, could the quantum system outperform the classical system? Okay, so in particular, I want to focus on engines in the lab because a lot of what I've been doing has been focusing on how we can model these systems. And in the past decade, there's been a number of realizations of engines in atomic systems, in particular, basically the smallest you can get, single atom engines, and also many body engines. And I wanted to just quickly highlight that a lot of these systems are done essentially in the adiabatic limit, i.e. quasi-static or extremely slow. And what I've been trying to do is essentially take these two non-equilibrium scenarios. And in particular, non-equilibrium many-body scenarios. So we want to explore quantum heat engines in many-body interacting systems in particular, to understand how they scale with increasing the number of particles in your system. And there are a number of quantum effects that only really occur in many-body interacting systems, and to see whether these can enhance the performance of our engine cycles. And I'm going to go a bit more into what our engine cycles actually are in just a second. But I also wanted to highlight that if you're working in the adiabatic limit or quasi-static limit, essentially you have zero power output because you're running your cycle incredibly slowly. And so essentially, to get finite power output, some sort of meaningful power, we require non-equilibrium scenarios, i.e. require non-equilibrium simulation. Okay, so I wanted to go over a particular example of an engine cycle, which maybe some people are familiar with, usually taught in undergrad thermodynamics. So you start with, for an Otto engine cycle, you essentially, I'm thinking of some sort of harmonically trapped quantum system. It doesn't have to be quantum, but we're focusing on quantum systems here. So essentially, beginning in some sort of low temperature equilibrium state, i.e. this blue point in the lower left of this figure, we have control over the harmonic trapping frequency. And essentially what we typically do is, starting from this equilibrium state, we perform some sort of unitary compression stroke, i.e. we compress the gas and put work into the system. The second stroke of this 4-stroke engine cycle is going to be, you connect to some sort of high temperature thermal bath and you take in heat. And then essentially the rest of the cycle is basically reversing the first two steps. So once you're in the high temperature equilibrium state, we are going to disconnect from the thermal reservoir and expand the gas and reducing the energy of the gas and getting some sort of work output. And by convention, work input is going to be positive, work output is going to be negative because it's work done by the system. And finally, to complete the cycle, you essentially connect with that low temperature reservoir and you go back to your initial equilibrium state. This is what I mean by some sort of cyclic process. And usually we monitor performance by a combination of, let's say, the net work, which is just simply the sum of the work in and the work out. And if this is less than 0, it means that overall work has been done by the system. And we're also interested in generally in engine efficiency, which is just going to be the total net work divided by the amount of heat that you took in. Okay, so a good question is why we actually need generalized hydrodynamics. Also, I haven't seen many of the talks earlier last week, just because I didn't have a Zoom link. So I'm kind of assuming that most people are familiar with generalized hydrodynamics and what sort of systems it can model. But obviously, feel free at any time to stop me if there are any questions. So why we need generalized hydrodynamics? Well, if we're doing this 4-stroke Otto cycle in a non-interacting gas, we wouldn't need generalized hydrodynamics. But this sort of situation has been done before, and also we're mainly interested in how interactions may affect or even possibly enhance a quantum engine. So what we're going to do is we're going to add just your typical delta function or contact interactions. And this obviously complicates the scenario. So I've just drawn basically a parameter space partitioning the 1D Bose gas into various regimes as interaction strength along the horizontal axis, temperature along the vertical one, and we see we have a number of different regimes which we can model using different methods. So very strongly interacting low temperature we can model, or even high temperature we can model as a free Fermi gas, i.e. a Tonks-Jadot gas. Low temperature weak interactions, it becomes a quantum or thermal quasi-condensate. And we can use methods like C-field methods or stochastic methods to model this. And of course, at high temperatures, you effectively have an ideal Bose gas where the temperature, the kinetic energy essentially swamps the interaction energy. But we're generally interested perhaps not in just remaining in each of these particular regimes, but obviously moving outside of these regimes or even between these regimes. And that's really where generalized hydrodynamics becomes particularly useful for the sort of systems we're interested in. So what we're going to do is essentially that exact same Otto cycle that I showed before, where you're taking a system between two harmonic traps and then attempting to perform a cycle and get some sort of network output. And importantly, we're going to be doing a linear quench between these two harmonic trapping frequencies as a function of time. So we're only going to be focusing on simulating the unitary work strokes. Okay, I just wanted to highlight two kind of idealized limits of engine operation. The first is quasi-static. This is the one that's pretty commonly taught. And it is essentially when you take extremely long, it doesn't have to be infinitely long, but it's effectively infinitely long to do your work strokes. Because every step essentially relies on thermalizing your gas. This is the quasi-static limit, so it's very slow and effectively gives you 0 power output, because when you divide the network by the cycle time, even though network can be decently high, the total cycle time is extremely large and you effectively get 0 power. The other limit is the sudden quench, where you do these work strokes extremely rapidly. And if you do get beneficial network out, then you definitely have a finite power output, because you're basically doing this cycle as fast as you can. But essentially what we want to do is want to understand how this engine operates in between these two limits, and whether there is some maybe point where we achieve maximum power output outside of these two limits. And this is essentially where we need this generalized hydrodynamic simulation, especially if we're going to be working outside of one of those previously mentioned regimes where there are other methods. I also really wanted to mention that this isn't actually the first time that quantum engine cycles have been looked at in GHD. Like Alvis has looked at, in particular, the effects of pre-thermalization on quantum heat engines. Okay, so now I'm just going to move on to the results that we've obtained for non-equilibrium engine cycles, non-equilibrium Otto cycles in a one-dimensional Bose gas. Okay, so the particular thing that we've been focusing on is how the performance depends on the regime that you're in. And because there are a lot of parameters in these quantum engine cycles, we are going to fix some of them. We're essentially going to fix the high temperature, the ratio of the high and the low temperature equilibrium states to be 1.5. We're going to fix the ratio of the harmonic trapping frequencies, this longitudinal harmonic trapping frequency, to be 1.2. And then we're essentially going to vary the time over which we do this, these quenches. And both quenches are going to be done over the same amount of time. And I've just highlighted the fact that we're focusing exclusively on engine performance here. So anything but, because there's a negative sign on the work, and this is also normalized. This is in harmonic oscillator units, just some sort of natural units. And we've also normalized to the total atom number in our system because we wanted to be at least reasonably realistic to experiment. And in the weakly interacting regime, you tend to have about 2,000 atoms in your system, whereas in the strongly interacting regime, you can be limited to about 20. So to compare fairly, we're normalizing also to the total atom number. So if this is greater than 0, then we have engine operation. Anything else, we're kind of going to ignore it for now. So the first case we're looking at is essentially a very strongly interacting system. And we see that basically this doesn't really operate as an engine. We see this sort of, when we do this, the quench is extremely fast. This quench time TQ extremely fast. We essentially see a plateau to some sort of performance as a sudden quench. And then if we do it extremely slowly, reaching the adiabatic limit, we will eventually get engine operation. But as we're focused on finite power output, we're again not really interested in the quasi-static limit. So a good question would be, okay, what happens if we go to higher temperatures? And at higher temperatures, we see a significantly, well, relatively significantly larger net work output. And it seems to operate as an engine regardless of the total cycle time or the quench time. And then if we go to weak interactions, finally, we are going to see a similar performance to the strong low temperature interactions, except the sudden quench results are quite a bit lower, and the adiabatic, it sort of, at very short times, it reaches a fairly significant work output. And this is kind of the first interesting thing that we found. We observed this rather sudden rise in the network at relatively short times, regardless of regimes. And this is going to be fairly important when I talk a bit more about the power output later. Okay, so finally, I wanted to go from stay in the weakly interacting regime, but increase the temperature because we generally saw an increase to the performance in the under increasing temperature for the strongly interacting regime. And I had to actually make a new plot because we see a significant rise in the overall network that we achieve at high temperatures in the weakly interacting regime. And again, interestingly, we see this sudden rise in the overall network at relatively short times, which is perhaps surprising because you would generally think that the convergence to the adiabatic limit is typically considered to be rather slow. But what we see here is essentially quite a sharp rise and then a slow, basically a plateauing and then a slow transition to essentially thermal performance or quasi-static performance. So that's rather interesting. But another very key parameter is also going to be the efficiency. Now, we kind of want to understand how well this engine performs. So it's not just about network. We also want to consider the efficiency, which is going to be the network divided by the overall amount of heat that we take in. Now, we're just looking at the systems that actually give positive network outwards. And we see that regardless of regime and regardless of temperature, relatively similar efficiency. But the real question is actually, how does this compare to your typical bounds on efficiency? And that sort of gives us an indication as to whether we actually want to pursue these sorts of engine cycles. Okay, so the maximum possible efficiency is essentially just the Carnot efficiency. And it's a rather interesting fact that these sorts of classical efficiency bounds also apply in quantum systems. And that has a lot to do with the fact that we're working between two thermal states, and the fact that, of course, the second law generally applies regardless of system. But essentially, if we were to compare this against the maximum possible efficiency, so this is our maximum efficiency of the best one that we found. Essentially, we're working a little bit below half the Carnot efficiency, which isn't bad, but it's not ideal. But we generally don't expect these sorts of cycles to be working anywhere near the Carnot efficiency. And this is generally significantly better than most finite time quantum engine cycles. But again, it's not particularly fair to compare the efficiency of this system against this idealized limit of the Carnot efficiency. So what we're going to do instead is actually look at the power output that we're generating from this system. So another classical result that still applies in quantum systems is this efficiency at maximum power of a Carnot engine cycle. And essentially, this is classic work by Curzon and Albon, which identifies the point of maximum network or maximum power. And then it's a slight modification from the Carnot efficiency, where instead of 1 minus TL over TH, it's 1 minus the square root of these things, which for our system would be 0.18 for our temperature ratio. But to apply this, we actually need to figure out where the point of maximum power actually is. And this is somewhat difficult because it requires an estimation of how long these systems take to thermalize, because the power output is simply the net work divided by the total cycle time. So we have control over the quench time, but this thermalization rate is pretty difficult to obtain because we'd need some sort of model for an open quantum system. It can be done, and we have done it in the quasi-condensate regime using stochastic methods. But here, just as a simple application, we're going to assume that the thermalization rate is approximately on the order of the natural time scale of the harmonic trap. We would need to do a bit more work to see whether this is actually feasible. But considering that we're coupling to essentially thermodynamically large baths, this is a limit that's been used before. And we find that our results don't actually change that much when we vary this time scale by about an order of magnitude. So we're going to make an assumption on how long this Otto cycle takes to run. And if we use this assumption, we can find that power output for essentially, I'm sort of reducing the space down to our best result for the high temperature weakly interacting system. And we see that there's this quite sudden rise in the total power output at fairly short times. And this is, again, associated with that sudden rise in the network at fairly short times. So now that we've got our maximum power, we can essentially find our efficiency at maximum power. And comparing this with the more applicable Curzon-Alborn bound on the efficiency, we see that it actually achieves pretty significant efficiency compared to a lot of other results in the field. And more generally, this is really only applicable, or this is really only able to be found by using generalized hydrodynamic simulation, because we're operating essentially outside of the bounds of more established previous methods, like stochastic methods, to simulate this system. All right. So that's basically the core of what I wanted to talk about today. So as a quick summary, I wanted to give a bit of a motivation as to why we're interested in using generalized hydrodynamics to study non-equilibrium quantum thermodynamics. We've observed this general performance boost at fairly short times, which I don't believe has been identified before for this system. And we've also seen that GHD, or finite time simulation, actually enables calculation of this efficiency at maximum power. And we see this point of maximum power at quite early times. As a final note, I just wanted to point out that generalized hydrodynamics is actually quite applicable in quantum thermodynamics for simulation of perhaps even fully non-equilibrium engine cycles or fully pre-thermal engine cycles, where we never give the system time to actually fully thermalize at any point. We're very interested in working between these regimes, where generalized hydrodynamics is essentially the only thing, as far as I know, that can do this at finite temperature. And also, engine cycles using other integrable or near integrable models are extremely interesting. And so, yeah, that's basically all I wanted to say. And thank you.
Thank you, Raymond, for the nice talk.
Thanks.
There's a question.
Hello. Yes, I have a question, like in the concept of a cycle in quantum systems. Like, is it true that in the cycle at the end you reach back to the initial state, or is this not that important? You just need that the average energy is the same as what you started, or?
So there is a number of situations where, so it really falls into two categories. What I'm looking at is where you exactly, again, reach your initial state. And this is similar to classical engine cycles or idealized cycles. You don't, in general, require that. And there's a lot of interesting work being done on cycles where you essentially never truly reach equilibrium. And this sort of leads naturally to the concept of limit cycles, where you basically just keep doing the cycle without ever reaching equilibrium. And it's possible that you could achieve some sort of performance boost, because those sorts of systems are essentially not bounded by your typical thermodynamic inequalities.
I see.
So it's very interesting to look at those sorts of systems.
But it's also not obvious to me, even if you do it adiabatically, that in the quantum system you reach back the initial state, and then the question would be what will happen when if you do it at a finite rate. It's not easy to understand that it comes back to the same state to me.
Absolutely, absolutely. And that's something we also essentially have to look into. If we're talking about this thermalization strokes, that's definitely a question that we're very interested in, whether it's even technically feasible to reach the same, to reach thermalization in a finite time in these sorts of open quantum systems. So that's definitely an interesting question, but something that we have only looked into a little bit.
Okay, thanks. That was a nice talk. Thank you.
Thank you.
Hi. Maybe you can clarify a bit how this is dependent on the integrability of your gas?
Yeah, so this essentially the whole setup is it's not the cycle obviously isn't strictly dependent on the integrability of the gas, but the actual working fluid that we're interested in is the underlying model without the harmonic trap is integrable. Obviously, it's just the 1D Bose gas. And we have some more work to essentially understand how the underlying integrability of the model actually affects the performance of this cycle. So really, this is just some initial work that we've been doing looking at these systems and utilizing generalized hydrodynamics because it's essentially the only thing that can simulate it in these regimes. I hope that sort of answers your question.
I say yes on Jacopo's behalf. Hi, Raymon and
Okay.
Lisa. Maybe I'm the next one asking a question.
Hey.
I find very interesting this increase of the power of the cycle that clearly has to do something to do with the trapper, but I'm not understanding if there is a simple picture to understand why we expect that at that time scale.
Yeah, no, that's a great question, and that's something that I've been essentially working on trying to understand. And it essentially seems to be, my initial intuition was that it might have something to do with the natural frequency of these oscillations, but then it seems to be fairly regime independent. Like you would expect some kind of difference between the quasi-condensate and Tonks-Jerdaux regime. I don't currently have a simple picture as to why that is the case, but that's absolutely what I'm looking into, because it seems to be the most standout feature of these sorts of systems. Yeah, I don't have any more detailed answer to that, but it is definitely, it is kind of the key thing that we're looking into right now.
I kind of wonder what does it happen trap that is not harmonic, so it doesn't have only one frequency, but is anharmonic and with more frequencies, and that could be
absolutely.
I do not. It could be a very different picture.
It definitely could be. There's a lot of work that we're currently doing on that, just because it's somewhat more complicated by the fact that it's not just like a sudden quench and then this gas is oscillating. It's this continuous driving, which it seems has this predominant effect of basically having this increase to the network at such at this characteristic time of about half the natural trapping frequency or the natural trapping time. But yeah, no, it's definitely an interesting question.
Okay, thank you very much.
Thank you.
Hello, thank you very much for your talk. I wanted to ask you one question. The Carnot bond is fundamental, of course. The Kirchner-Alhorn bond, as far as I understand, is more phenomenological. It's nothing fundamental. It depends on how you model the exchanges of heat.
It's technically for an endo-reversible cycle, yes.
So do you think there could be some quantum engine who could do better than Kirchner-Alhorn? There's nothing which prevents that.
Absolutely. It definitely could be, in the sense that you're correct. There's nothing fundamental that prevents it. And it's sort of, maybe I should have, I usually try to present it more as like a benchmark rather than a bound. I might have accidentally said bound a couple of times, but so there's definitely feasibility for surpassing that. With an Otto cycle, it might be difficult, but with something like a quantum Carnot cycle, although I guess that relies on the adiabatic limit. But yeah, no, absolutely. It is not ruled out, I will say, that you could surpass that.
Thank you very much.
There's another question.
Hello, thank you. Thank you for the talk. I had a couple of questions. So the first one is, so essentially you're doing a thermodynamic cycle with the work strokes being a quench. So I was wondering if you're doing it in the adiabatic limits, and have you compared the efficiency between these two cycles?
Yes, so we have compared the efficiency, but I did not have those results on hand, unfortunately. It is quite simple to compare this with the adiabatic efficiency for this case, just by considering some work strokes that are essentially entropy conserving. I basically compared it with the Carnot cycle, as it's more commonly known. But yes, absolutely, you can fairly easily compare it to the adiabatic efficiency of this same cycle. Yeah, and that's what we're planning on doing.
Okay, right. My second question is about statistics of the system. So here you're essentially working with the Bose statistics, yes?
Yeah, essentially.
Yeah. So I was wondering if you start with the fermionic system, say in the Tonks-Girardeau regime, or essentially with a Gordon-Yang model, would you have efficiencies, I mean, higher? Would you have a better gain in the performance of the engine?
If we worked with a Tonks-Girardeau gas rather than a quasi-condensate, well, we generally don't see. We see that the Tonks-Girardeau gas performs fairly poorly. So this, which one is it? The purple line on this figure. It has a fairly low efficiency and low network output, but that really requires a bit more investigation as we go to higher temperatures. And it is also another thing that we've done that I didn't have time to show is compare it essentially to a perfectly free Fermi gas to see or the sort of limit of the performance in that case. But so far, it seems that in general, the quasi-condensate regime kind of operates a bit better. And this isn't unfounded. There has been some previous talks on very few body, not talks, papers on very few body engines where bosons naturally outperform fermions in the case of the efficiency of an Otto cycle. But so it seems like whether this is something fundamental or it scales to many body systems, like a large amount of atoms, is something that remains to be seen.
Okay, thank you.
Thank you.
I guess you've addressed all the questions.
Okay.
Thank you for the talk.
Well, thank you for having me.